Today we'll look at equipotential lines, and these are those blue lines over here, which help us determine the characteristics of an electric field. And in 3D, these blue equipotential lines are basically equipotential surfaces. So as we can imagine, given that the electric field of this positive charge has a magnitude of 1 over 4 pi by the permittivity constant, and that's multiplied by the charge magnitude over the square of the radial distance from the charge. And we know that the potential for a positive charge is defined as 1 over 4 pi epsilon naught, and that's multiplied by Q1R. So therefore, if the radial distance to the charge is the same, then the potential is constant. So these equipotential lines are basically called lines of equal potential. So in this case, we can see that VA is equal to VB because they have the same radial distance from the charge. And the equipotential lines are always perpendicular to the electric field. And one thing is that they tell us that the relative magnitude of the electric field can be determined by the gradient of the potential lines. So when those equipotential lines are close, the electric field is stronger, and as we move away, the potential lines are further apart, which indicate that the electric field is weaker. So from this simple relationship here, we can see that the electric field is equal to the negative of the gradient of the potential. So if you were to differentiate V with respect to R, you're going to get minus 1 over 4 pi epsilon naught by Q on R squared, and then putting a negative sign behind that, we get the electric field. And as we mentioned, the direction of the electric field is always perpendicular to the equipotential line. And also the electric field points in a direction of decreasing potential. So as we can imagine, as this radial distance gets bigger, the electric field gets weaker. And if we recall that the change in electric potential energy was equal to minus the work done by the electric force, which is the dot product between the electric force and the displacement vector in the radial direction. So as we've shown, for a conservative field, the change in electric potential energy is equivalent to the work done by the electric field. And we can write this here as minus the integral of the test charge by the electric field dot dr, and that's equal to the change in electric potential energy. And if we divide through by Q, we get the change in electric potential. So basically, if we differentiate the electric potential with respect to R, we get rid of this integral and we get back the electric field, which is this relationship over here. And looking at a few more general examples, so over here we have the electric field for a dipole. So close to the positive charge, we have spherical equipotential lines, because as we can see, the electric field is perpendicular to those lines. And in the middle we have an equipotential line, because the electric field is perpendicular to this line, and if we draw a radial vector to this line, because this radial distance of the positive charge is the same as the radial distance to the negative charge, then we can see that the electric potential along this line is all zero. So that's true if we draw a radial vector here and a radial vector to this charge. So R plus is equal to R minus, and therefore the potential all on this line is zero. And if you can imagine that if we look at this equipotential line, then the potential along this entire line is the same. Because for a dipole, the potential is equal to 1 on 4 pi epsilon naught by the positive charge on R plus, and then plus 1 over 4 pi epsilon naught by the negative charge on R minus. Okay, so along this vertical equipotential line, R plus is equal to R minus all the time, but where R plus and R minus are different, such as along this equipotential line here, the potential is not zero, but it's the same for all of these points on the line. And here is another example for a uniform electric field where the equipotential lines are perpendicular to the electric field. So really have a think about that, and that's how we visualize electric fields from equipotential lines. And I'll see you in the next video.